Hey, Honors Pre-Calc. Today we are going to be doing lesson 5.1, trig parent graphs. The essential question for today is how do you identify the six trig parent graphs and how do they compare? So you've already kind of built sine and cosine curves or waves from scratch. So today we're going to look a little bit more at those and then the other four trig functions. That's tangent, cosecant, secant, and cotangent. So you will graph the six trig function parent graphs. You will understand the relationship between the max, min, zeros, asymptotes of a trig function in the unit circle. And you will understand the relationship between the max, min, zeros, and asymptotes of a trig function to another trig function. You already know a lot about trig functions and about the unit circle, so this just continues to build on that knowledge. And by the end of this lesson, you'll be able to answer a question like this. The absolute maximums of sine coincide with the relative minimums of which other trig function graph? All right, so I'm going to take us over to the notes and we are going to get going. All right, so here up at the top of the 5.1 notes, you see that we have copies of the sine and the cosine waves. And this is exactly what we saw the other day, right? And we know that this is one period of sine and this is one period of cosine. But we know that they keep going, right? So this keeps going like this, and this keeps coming back down like that, right? But for our purposes, it's we really understand the whole graph as long as we have one period. And it's most common to see from 0 to 2 pi graphed. For our purposes, we're going to say that there are 5 key points on each one of these graphs, and the x values are 0, pi over 2, pi, 3 pi over 2, and 2 pi. And those are for when you're plotting sine and cosine parent graphs. We want to see at least those points, and then the rest can kind of be a rough sketch. So I'm going to plot these points on our curves here, and I want you to do the same. And if we wanted to make a chart of the 5 key points for sine, the x values would be as given. So 0, pi over 2, pi, 3 pi over 2, and 2 pi. And the y values are going to be pretty simple, right? At 0, we have a y value of 0. At pi over 2, we have a y value of 1. At pi, we're back at 0. At 3 pi over 2, we're down at -1. And then at 2 pi, we're at 0. So those are the key points that we always want to plot before we kind of complete the curve. And when we get into lesson 2 of this unit, we're going to see how we have some transformations like stretches, shrinks, shifts for these types of graphs. So it's going to be really important that we plot those points. For cosine, it's pretty similar. The same x values, but the y values have shifted. So we have 0, pi over 2, pi, 3 pi over 2, 2 pi. And now the y values start at 1, go to 0, -1, 0, and back to 1. Okay, so that's what we want to remember. We could also write down the domain. We can write down the range for these. Let's actually do that. We did see that the other day, but I think it's going to be good to have it in our notes. So for sine, the domain we know is all real numbers. The range is from -1 to 1. The amplitude is 1. And the period is 2 pi. Remember, the amplitude means the maximum extent of a vibration or oscillation measured from the position of equilibrium. In other words, it's this length right here from the center line or the midline or the equilibrium line up to the highest point away or the lowest point away from that line. So this is the length of 1. This is a length of 1. So the amplitude is 1. The period is what's the x distance before the whole thing starts to repeat itself again. And that's going to be this whole 2 pi. Right here is where it starts to start over. And the cool thing about sine and cosine is that they have the exact same domain, range, amplitude, and period. And you saw that the other day. Now, the other day we saw exactly where sine and cosine come from, these curves, right? They come straight from the unit circle. The sine represents the y values as you rotate around the circle. The cosine represents the x values as you rotate around the circle. I'm not going to go through that again, but hopefully that makes sense. We will come back and look at that a little bit more in class. But today we are going to spend most of our time looking at the other 4 trig functions. That's tangent, cosecant, secant, and cotangent. On your notes, the first one is tangent, but we're actually going to skip it. I want to look at cosecant first because I think cosecant and secant go together pretty nicely when you're thinking about sine and cosine. Then we'll come back to tangent. So for cosecant, remember this is at the bottom of your page if you have this printed out. So make sure that you skip tangent, right? We're starting with cosecant. So for cosecant, this is abbreviated CSC. We should know that. So if you wanted to graph this on your calculator, first of all, you would have to type in 1 over sine. Because we don't have a cosecant button, at least I don't on my graphing calculator. And cosecant is 1 over sine, and that's exactly what happens when we graph it. If we think about it as being all of the y values are reciprocals of what they were for sine, that'll help. So the dotted curve that you see on this graph is sine. It's the original sine function that we already sketched from 0 to 2 pi. You can see it goes up to 1, back to 0, down to -1, back to 0. Excuse me. Okay, so that's sine. So if we think about what cosecant would be, anytime that the y value was 0 in the sine graph, think about what happens if we flip 0, if we take the reciprocal. If you take 0 over 1 and flip it, now we have 1 over 0. And we know we can't divide by 0. So anytime that the sine function had a y value of 0, it's going to be causing these asymptotes because we can't have a value once we flip it. Okay? If the y value was 1, what happens when you flip 1? Well, you still get 1, right? The reciprocal of 1 is 1. So that's why the graphs intersect here. And the reciprocal of -1 is still -1. And then think about what's going to happen for all these other values. Let's say we take the value 1/2. If you take the y value of 1/2 and flip it, you're going to get 2. So you can see all of these other fractions or decimals in here. Once they flip, they're going to be getting bigger and bigger. So that's what causes this curve. And this solid curve is the whole cosecant graph. So you have sketched one full period of cosecant when you have one upward facing U curve and one downward facing curve. That's one period of cosecant. And this is not a wave function like sine and cosine are. It's a much more interesting or bizarre looking function. But that's one period, and then it starts over and does the same thing again. The dotted curve is not part of the cosecant graph. That's just there for reference because it's showing us sine. So hopefully that makes sense. For cosecant, the period is still 2 pi. You can see from 0 to 2 pi here is when it restarts and does the upper facing curve again. The domain, this time, it's going to be almost all real numbers except for where all of these asymptotes are. So we have an interesting way of writing that. I'm going to use the double line R, which means all real numbers. In case you're not familiar, I'll write it on the side. But we know already the answer is not all real numbers. So how we express that is we write all real numbers, x does not equal pi over 2. And that's just kind of saying except. So all real numbers except x cannot equal pi over 2. That wasn't right, was it? I messed that up. I was looking at the wrong one on my page, sorry. X cannot equal, and there's an asymptote right at 0, right? So I'm going to put 0. In fact, let me get my white out here so this looks nicer. Okay, so it's 0 is where one of the asymptotes is. Okay, and it is, we're going to write plus or minus n pi. And what that means is if I add or subtract any whole number of pi's, I end up at another place where there is an asymptote, and that is another spot that's not part of the domain. So if I add 1 pi, I get to here. If I add 2 pi, I get to here. If I subtract 1 pi, I get to here. If I subtract 2 pi, I get to here, and so on and so on and so on. That's an easy way to account for every asymptote. The range this time is going to go, if we kind of go up the y-axis, everything is included until here. There's a big gap between -1 and 1, and then it picks up again. So we're going to write that like this. And the vertical asymptotes are all those places that we left out of the domain. So we would write that as 0 plus or minus n pi. This last question here, I want you to definitely think about this. What causes the function to be undefined at the vertical asymptotes? Well, we've already kind of discussed that. It's because cosecant is 1 over sine. So vertical asymptotes exist when sine of x equals 0. So now we have it in writing. All right, so if that made sense, then secant is also going to make a lot of sense because secant is pretty much just a shifted version. Just like cosine is a shifted version of sine, secant is going to be a shifted version of cosecant. So let's flip over to that. So secant here, the dotted curve represents cosine this time. And you can see from 0 to 2 pi, we have the cosine curve here. And so what we do here is anytime that cosine crossed the x-axis and had a y value of 0, that's going to cause us to have these vertical asymptotes because we can't divide by 0. And then we have some spots where cosine and secant intersect at 1, y values of 1 and y values of -1 because the reciprocal version of 1 is still 1. The reciprocal version of -1 is still -1. And then just like with cosecant, we just kind of curve the opposite direction. So what I am sketching right now is one exact period of secant. We still go from 0 to 2 pi, and this time it is just 1/2 of an upper curve, a full lower curve, and then another half of the upper curve. And that's just so that we still stay from 0 to 2 pi as one period. So the period is still going to be 2 pi. The domain this time is going to be all real numbers, except pi over 2 plus or minus n pi. That's where I got that pi over 2 from earlier. So you can see the first asymptote's at pi over 2. We add or subtract any number of pi's, and we get to another vertical asymptote. Okay, so that's an easy way to account for all of those breaks in the domain. The range is going to be from -infinity to -1, including the -1, and then pick it back up again at 1 and go to infinity, just like with cosecant. And the vertical asymptotes we can steal straight from the domain. And then this question here, what causes the function to be undefined at the vertical asymptotes? And this happens because, as we know, secant is 1 over cosine. I could have even written that up here like I did earlier. So the vertical asymptotes exist when cosine equals 0. Okay? So that's how cosecant and secant work. If you try to graph 1 divided by cosine or 1 divided by sine on your graphing calculator, you'll see these weird looking U-shaped curves just like this. And all you need to know for now is what they look like. We're going to study them more in depth later. But let's now take a look at tangent. So I'm going to flip back over to the front. We're going to go back to the graph that we skipped earlier. Tangent graph. So this one looks a little bit different as well. There's all these weird looking slopes that just keep restarting. And this comes from the unit circle. Because remember, tangent, if we think about unit circle land, tangent was y over x, right? But if we think about how sine on the unit circle Sine of theta was y. Cosine of theta was x. Tangent theta was y over x. So technically, we could also say that tangent of theta was sine over cosine. And I would like you to kind of write that on the side somewhere in your notes. Because if you think about that, y is equal to sine, so we could replace this y with sine. X is equal to cosine, so we could replace this x with cosine. And that gives us a good way to graph the tangent functions, because tangent is really equal to sine over cosine. So for every x value on this tangent graph, think about that we're taking the output from the sine curve and dividing it by the output from the cosine curve. It's initially a little bit weird, but I'll show you what I mean. So one period of tangent is going to be considered this kind of central curve right here. That's what we're going to consider one period. So it's going to be pi this time, and it's going to go from negative pi over 2 to pi over 2. But let's see how this is actually created. So I'm actually going to jump to the last question here. What causes the function to be undefined at the vertical asymptote? So let's think about that. We know tangent, just like we said, is sine over cosine. So if something is going to be undefined, it's because in the fraction, the denominator is 0. So in this case, the denominator is cosine. So when cosine is 0 is when we're going to have vertical asymptotes. So vertical asymptotes exist when cosine equals 0. So if we take a look back up at our initial cosine curve, we had a y value of 0, or we crossed the x-axis at pi over 2 and 3 pi over 2. So you can see we have those vertical asymptotes here. And then we just have to think about, okay, what is going on at all these other spots? So let's think about the x value of 0. At the x value of 0, if we're going to do sine divided by cosine, it would be what? A y. We're thinking about what are all of the y values on these graphs. So we have 0 divided by 1, right? Because if we think just always x values of 0, what's the output of sine? A y value of 0. What's the output of cosine? A y value of 1. So we're going to do 0 divided by 1. That's 0. So that's how we have this point right here. We could keep going and try other points, but really at this point, all you really need to see is that this is what the tangent graph looks like. When we meet in class, we will talk more about where this comes from. Yeah, so we're going to see some animations with the unit circle at some point, but I'm just going to kind of make sure we have this all filled in right now. So for the domain, this time we have all real numbers. X does not equal pi over 2 plus or minus n pi. For the range, this time all real numbers from negative infinity to infinity are part of the range. And our vertical asymptotes happen at those same spots from the domain. Okay. There is one more thing I wanted to point out here. We have key points for the tangent graph. So I'm going to create a chart. And it's going to go from negative pi over 2 to pi over 2, splitting it into fourths. So we're going to have negative pi over 4 and pi over 4 as well. And let's fill in these y values. So at negative pi over 2, that's a vertical asymptote. So there's no y value. At negative pi over 4, we're actually at a y value of negative 1. 0 is a y value of 0. Pi over 4 is at positive 1. And then we have another vertical asymptote. So that's going to be something that we're going to need to know at some point. So I wanted us to have that written down. Okay. And that is good enough for now for tangent. Since we are here, I do want us to have key points written for cosecant and secant as well. So let's kind of fill that in while we're here. Cosecant is going to go from 0 to 2 pi. just like sine and cosine. But this time it's going to be kind of weird because 0, pi, and 2 pi were all vertical asymptotes, if you take a look at the graph. So the only thing we need to know is that pi over 2, we're at a y value of 1. At 3 pi over 2, we're at a y value of -1. We're going to do the same thing for secant, and then we're going to look at cotangent. Okay, at 0, we're at 1 this time. Pi over 2 is a vertical asymptote. At pi, we're at -1, and then another vertical asymptote, and then we have a y value of 1. And now let's take a look at cotangent. Cotangent has a kind of flipped version of tangent and shifted. This is one full period. So the period is pi. And this time it goes from 0 to pi is the first version of that period. The domain is all real numbers except for the vertical asymptotes, which happen at 0 plus or minus n pi. The range is going to be from -infinity to infinity. The vertical asymptotes are at those gaps in the domain. And let's kind of back up then and think about the big picture here. Cotangent is the flipped version of tangent. I told you that tangent was sine over cosine. So cotangent is going to be cosine over sine. So since cotangent equals cosine over sine, that tells us that we are undefined at the vertical asymptotes because that's when sine was equal to 0. Okay? And you can see that if you look back at the sine graph again, okay? This time it's just kind of flipped logic of with tangent. Again, we will talk more about these and see some animations when we get together in class. All right, let's just fill in these last 5 key points and then we'll be done. So this one goes from 0 to pi. I'm going to split that into fourths. So it'll be pi over 2, pi over 4, and 3 pi over 4. I just know that because I'm just using fractions here and just plopping pi into the numerator, right? So it's 0, a fourth, a half, 3/4, and then 1. I just split 1 into fourths, really. And the y values are going to have vertical asymptotes on the edges, because that's here and here. And then at pi over 2, we have a y value of 0. At pi over 4, we have a y value of 1. At 3 pi over 4, we have a y value of -1. Okay? So that's what you would need to plot if you were going to sketch this from scratch. And that is it. So those are the 6 parent graphs of trig functions. They're a little weirder than a lot of the other functions that we've studied so far this year. And we're going to see how to transform these and look at a lot more properties over the next few days and weeks. But thank you so much for watching. Make sure you submit on Schoology and have a great day.